Okay, back to the vector drawing and component problem that we were given when we left. First, for part capital A up here, which has, confusingly enough, lowercase a and lowercase b parts to it. In lowercase a, we're supposed to draw a vector whose tail is at the position x equals 1, y equals 3, right there, that has components minus 4 and plus 1, x component minus 4 and y component plus 1. Okay, and a similar thing for this, except the signs are switched on the components. So let's go over to the solution now. For starting at 1, 3, that's right there, I need to go to the left by 4 units. In other words, start at the tail and move to the tip by first going only along x by minus 4 units. 1, 2, 3, 4. That gets me down there to x equals minus 3. And then along only the y direction by 1 plus 1 unit. So I go up by 1. That gets me to there. So the arrow that we're drawing is like this. Okay. Similarly, you don't need to put in that angle right here for this particular part. Just look at the arrow that I've drawn. Similarly, if dx is plus 4 and dy is minus 1, starting at 1, 3, that means I should go up by 4 along the x direction and then down by 1 in the y direction. So that gets me to there. So this arrow that I've drawn starting there and ending down there is the answer for part lowercase b. Now going to the second part, from that information we're supposed to find the length of those vectors. And in this case, we can really, even though the components have minus signs associated with them, in other words, dx and dy might have negative signs associated with them, we can still kind of use the Pythagorean theorem, because we know the Pythagorean theorem says the length of this vector is equal to the square root of this distance squared plus this distance squared. Now, this x component happens to be negative here, but when we square it, the minus sign goes away. So we can just think of the answer is the length of the vector d is the square root of the length of the vector is the x component squared plus the y component squared square rooted. And when we do that in this case, we get the square root of 17. I didn't really put units on this, but maybe if x and y were in meters, then this would be in meters as well. And of course, when we do that, the length of these two vectors are the same, and just because when we square minus signs, they go away, we get the same answer, which of course makes sense. Looks like these two vectors should be of the same length from the drawings up there. The length of both of them is the square root of 17. Not worrying about units here because I didn't put units on the axes. The interesting thing comes in when we try to calculate the angle. Now the angle that we're looking for here relative to the plus x direction going away from the tail location, the angle theta that we're looking for looks like this here, right? Here, starting at the tail, plus x direction goes like that. We go up from there and around until we hit the vector. That defines what that angle theta is. So it looks like it's a little bit less than 180 degrees. And in the second case, the angle is either a small negative angle, or you could think of as a positive angle that's very close to 360 degrees. But those would be equivalent ways of describing what that angle is. So here when we calculated the length of the vector and we got the length of the vector, we could just use the components in the Pythagorean theorem, ignoring the fact that they were negative signs. The question is, can we do the same thing here? When I used tangent theta as opposite over adjacent, we were always assuming that that angle theta was between 0 and 90 degrees. In other words, it wasn't a really big angle like this. And it was never a negative angle either. It was always some positive angle between 0 and 90 degrees. The question is, can we write down this relationship, tangent of theta is equal to the y component of d over the x component of d, with the signs thrown in there, and expect to get the correct angle by taking the inverse tangent of both sides? So once we found out the components, can we just take the inverse tangent of dy over dx? And if we do it in this second case, the case on the right, where the components are right here, we're expecting a small negative angle. When we take the inverse tangent of -1 over +4, we get an angle that's about -14 degrees, and that seemed to make sense, right? It's a small negative angle going down in the clockwise direction from the theta equals 0 direction. The problem is, when we do it in this other case, of course, -1 over 4 is the same number as 1 over -4. They're both minus 0.25. So when we take the inverse tangent in our calculator, we shouldn't expect anything different over here. And we also get -14 degrees. And looking at this angle here, -14 degrees is clearly wrong. So either we're making a mistake by using the components with their signs in there, or we've got to be a little bit more subtle about it. And the answer, or the way to think about it, is that we actually can use the components as long as we're a little bit careful about it. So let's look at this function. This relationship that I wrote down here came from the relationship tangent of theta is dy over dx. Let's look at the function, the shape of the function tangent of theta, which maybe you haven't looked at in a while, but it probably looks familiar. In between these vertical asymptotes, which are at -90 degrees and plus 90 degrees, the tangent snakes from minus infinity up through 0 and then up to plus infinity. And so that's a 180 degree range there. And then over the next 180 degrees, it repeats. And over the previous one, it repeats, and so on. It's just a periodic function like that. So let's suppose we know that the tangent of the angle that we're interested in is minus 0.25, right? And we take that at face value. What that means is we know the output of the tangent is -1/4. Well, let's see, here's -1 down here. So if we go 1/4 of the way down to -1, it would be about the height right there. So we're saying the output of our function tangent of theta is -1/4. What we want to know is what is the theta that gave us that output. And the problem is there's an infinite number of thetas that could have given us that output, right? There's one value here that actually is about -14 degrees in this case, and it's very slightly negative. If we took this value of theta right there and took the tangent of it, we would get -1/4. There's another value which is 180 degree bigger than it, and it's a little bit less than 180 degrees. Take this negative angle value there, add 180 degrees, we'll get something a little bit less than 180 degrees. If you take the tangent of it, you'll get -1/4. And there are an infinite number of other ones. But notice that these two angles, this particular angle there and this angle there, are truly different angles. One of them is just a little bit below 0 degrees, and one of them is very close to 180 degrees. They're not equivalent angles. 1 degree and 361 degrees, I would say, are the same angle, but these are truly different angles. So when we're trying to solve this equation, tangent of theta equals -1/4, by taking the inverse tangent, we want to ask ourselves, if we take this at face value, is this true? Is theta equal to the inverse tangent of 1/4? Well, it is, as long as we're expecting an answer that's between -90 degrees and 90 degrees. So when you plug it into your calculator can't give more than one answer. In other words, there may be an infinite number of solutions to this equation, but your calculator is only going to give one of them. And the way it's designed is that it always gives the one between -90 and 90 degrees, which happened to be the correct one for that, the right-hand side part of the problem. It gives -14 degrees. That's the one angle between -90 and 90 whose tangent is -1/4. Now we may not be expecting that angle. Since the inverse tangent always gives something in here, if we're expecting an angle that's over here, we might have to add 180 degrees onto it to get to this other different angle. So you have to look at your vector and say, roughly where is the angle going to be? And if I'm expecting an angle between -90 degrees and 90 degrees, in other words, if my vector is pointing either up into quadrant 1 or down into quadrant 4, just above and below the plus x-axis, then we're expecting an angle between 90 and 90, and we would just take the inverse tangent. But if it points into quadrant 2 or quadrant 3, in other words, the angle is bigger than 90 degrees but less than 270 degrees, we're going to have to take the output of our calculator and add 180 degrees. Okay, so going back to this problem, here I'm expecting an angle between minus 90 and 90. I can just straightforward put it into my calculator and take the inverse tangent of the y component over the x component, and I get the answer I want. Whereas over here, I'm expecting an angle that is bigger than 90 degrees but less than 270, or I can think of my vector is sort of pointed up into quadrant 2, or maybe if it's pointed down into quadrant 3, those would be the cases where this isn't enough down here. I also have to add 180 degrees to get another solution that my calculator doesn't give me, and that gives 166 degrees. That makes sense, right? It's a little bit less than 180 degrees. So those are the two solutions there. I know that's a little bit complicated. There are other ways to do this as well, but this is probably the most common way to do it. So think of it as the upshot. To summarize, it's if you have a vector that has components fx and fy, it's always true that the tangent of this angle that defines the vector in polar coordinates is the y component over the x component. The question is it also true that theta is the inverse tangent of that? And it is true as long as the vector kind of points either up into the quadrant 1 direction or down into quadrant 4 direction, because then I'd be expecting an angle between minus 90 and 90 degrees. But if it points up into the quadrant 2 or down into quadrant 3 directions, I have to add 180 degrees onto what comes out of my calculator in order to get the solution I'm looking for. All right, one more thing before we stop and take a break here, and that is we've been talking about vectors and representing them as arrows, but there actually is one difference that you've already seen between arrows and vectors, and that is we said at the outset that vectors are defined by only having a magnitude and a direction. There's no such thing as saying where the tail should be located when you talk about a velocity vector. You know, when I specify a velocity vector, I might say, you know, I'm heading at 30 miles per hour in a direction 30 degrees to the east of north. To specify the velocity vector, I don't have to specify where my car is located in order to specify the velocity vector. So when we draw an arrow, of course, we have to draw the arrow starting and ending somewhere. So if I'm going to draw a particular velocity vector here in the xy plane that has a certain magnitude in a certain direction, we should think of these are all different arrows, but they all represent the same vector. So when we have an arrow that represents a vector, we're always free to take that arrow and move it around to some other location in the xy plane, and we should rest assured that we haven't changed the vector at all, because when I move it from here up to here, I haven't changed the magnitude or the direction of the arrow. Right? It's still pointing in the same direction in space in terms of orientation, and it still has the same magnitude. So you can always move your vectors around as long as you don't change the direction or the magnitude of them. All right, let's stop and take a break, and then I believe we'll get into some of the physics involved with these mathematical items.